So we have Uwe Stoll from Framatome, and the topic is going to be small modular reactors, a hype or reality.
Thank you very much, and thank you very much to give me the opportunity to talk about small modular reactors. Sometimes you hear SMR as small and medium-sized reactors, but I use this typical today, use small modular reactors. And I call the presentation a hype or reality, what's really going on. And first of all, most of the pictures and tables you will see are coming not from Framatome, they are coming from the Atomic Agency, and they are coming from the OECD, NEA, Nuclear Energy Agency of the OECD, where I'm both a member of. So I'm using this publication from this one, and not only to talk about Framatome products, but talk about what is going on the SMR. There exists a dashboard coming from the OECD, where we have a second edition coming out end of 2022. The next one will be end of 2023. It's not so much technical, but it talks about how close to the market are the different designs. From the agency, you have a more technical description about all these different steps or all these different design of small modular reactors. So you can find both of them in the internet. So first of all, the definition, what is a small modular reactor? From a small modular reactors, it's called a smaller, both in terms of power output and physical size, than a conventional gigawatt scale nuclear reactors. Typical, the power output is 300 megawatt. We have now a development of smaller ones in the scale of 1 to 10 megawatt electrical power output. Modular means it's designed to expect to favor modular manufacturing, factory production, portability, scalable development, and reactors because it uses fission. We are not talking about fusion, we are talking about fission. So, and I will start this discussion about with one of the main outcome from, I think, for the most of industry, but especially the nuclear, is the so-called the effect of scale. As bigger a reactor design is, as less the construction cost in, for instance, euros or US dollar per installed kilowatt hour. And this is the reason why on the today's market for the large powers, you see the tendency they are bigger and bigger and bigger. We are today with the modern design of EPR or Korean reactors, we are in a range of 1,500, 1,600 megawatt electric. We call this effect of scale. But when we are talking about smaller reactors, so you get a disadvantage in the economic drivers. And there's a lot of developments currently going on how to overcome this economies of scale. First of all, I call it modularization and factory build. Not to have too much weldings, too much construction on site. The best idea to have the whole, I call it in this time, primary circuit manufactured in the factory, and then as one piece delivered to the site and make a very first construction sign. The next step is design simplification. What it means when it's smaller, maybe you don't need so much systems, and to reduce the cost. Standardization, again, is something that means not to have a different design in different countries. This is the same as harmonization. To have, currently we have in the nuclear industry, practical different design requirements in the different states. So you have not one design you can build in Finland or UK or in France. You have all the different designs. And there is currently a lot of things going on in harmonization requirements that you can use the same designs in different countries, like we have it in the airplane industry. But this is a way how to overcome this economies of scale. Today, a nice picture, don't read it. I will always say these are all currently different designs that are on certain stage on application development. Some of them are operating, especially Russia and China are operating some of these small modular reactors. We have not so much in the Western world. And I always say small modular reactors, we are talking about icebreakers, submarines, aircraft carriers. All this has small modular reactors, but they are typical currently not so much used in electricity systems. We have this written design in Russia. Everybody have heard about Academic Lomonosov, where you have two reactors on a ship that is now located in Siberia. This is something what is operating, HTRPM. I come a little bit later on this one to explain it. Some explanation, we have typical water-cooled reactors. This is the most of these designs. They're I would say smaller reactors as the typical what we know today as pressurized water reactor, boiling water reactors. This type of reactors are typically limited in the temperature you can reach. We have at the outlet of the reactor maximum 330 degrees. This is some limit. Gas-cooled reactors, you can go to higher temperatures. As we have heard, there is an interest in chemical industry to have higher temperatures, so around 700, 800, 900 degrees. I've heard about the fast breeder. So this is some type of fast that is only 0.7% in uranium. The other one, fast breeders can also use the 238, so it needs better use of uranium. A very new development, but a very fast development, is the so-called microreactors. I will explain a little bit better what is microreactors. And there is molten salt currently deal with the waste. Sometimes they are called the waste burners because when we are looking on the waste coming out of a reactor, you typically have long elements with a long half-time. So the radiation is going several 100,000 of years, and molten salt reactors helps you to transmute these elements in other elements that only have radioactivity for the US as one of these one center you have in Europe, France, you have, but also Sweden, Finland, Denmark, and we have Argentina, we have China, Korea, Japan. So we had a lot of this headquarters of this SMR developers. Sometimes I make a joke that each university develop their own SMR, but to be attractive for students. A little bit different, but the same picture is picture in the countries and the different names of these developments. And you see that the typical countries like Russia, China are the most different design. Are in designs. So, and I will start with the development where my company is involved. It's the so-called NUWARD with a typical power output of 1,800 megawatt thermal power. In a nuclear power plant, you can say 1/3 of that will at the end electrical power. So we are in the range of 300 megawatt. Outlet temperature is 307 degrees. It was in development, but the EDF group, and Framatome is part of the EDF group, has decided that we will not follow this tendency further. So we stopped this tendency to put two reactors together to one turbine. Our idea is to use more proven design from the big reactors to have smaller reactors, as the other companies are doing the same what we today have with Westinghouse and GE and some others one, to make a smaller one of the big one and not a complete independent development. A good example for that is the so-called BWRX-300 in the US. This is a development of GE. This is a typical boiling water reactor. It's a small boiling water reactor. Here you see a lot of the things that all these SMR have. They are using natural circulation. They don't need pumps. So they don't need power in an emergency case. And they want to use proven components from the large reactors. They want to use the fuel from the large reactors. And they put most of the reactor building underground to be safer against external events. There's a very typical boiling water reactor. I call it a small boiling water reactor. The interesting in this reactor type is that it's currently built. So the preparation work, it's built. So the preparation work, the excavation work is going on in Darlington. This is an inside in Canada, and they're expecting to get the construction first. SMR built in the Western world. Here I put the Rolls-Royce SMR in because it shows, first of all, a little bit where I have a problem with, because the thermal power output is 1400 megawatt. What it means, the thermal power is close to 500 megawatt. So, and this is by definition not an SMR, but everybody calls the Rolls it is currently in the science has decided to use Rolls-Royce as the proposed small modular reactor evaluation program in Czech Republic. So this is a development I'm sure will be one of the first we will see in Europe. A typical pressurized water reactor, no very specific things. The next one is one of the type I put here as an example because it's different as the big one we have seen. So it's the so-called NuScale Voyager 12 in the US. The idea is here completely modular. You have not one reactor, but you can put more or less 12 modules together. Each of this reactor has 77 megawatt. You build it completely in the factory and then deliver this module on site. All the reactor together in one water pool to don't have anything like core melt. This is possible. You have natural circulation, passive system, use of proven fuel, and so on. But here you see, I put this one because we can discuss a very special thing. There was an released investment project in Idaho in the national lab in the US. And at the end, the cost of this type of reactor, so it means it was 6 modules together, around 500 megawatt electrical output, but the cost at the end was between $8 and $9 billion. And at the final end, short before construction starts, due to the high investment cost for this first of a kind type, it was stopped due to the high investment cost. So coming more or less to some other designs we currently have, I put here the so-called high temperature reactor module in China. This is a plant that is operating. It was entered commercial operation end of last year. It used helium and pebble bed fuel, a system that was developed in Germany in the 60s, 70s, operate as in so-called AVR in Jülich and the THTR in Ahaus. So, and we have this type, and here you come to outlet temperature of around 750 degrees. So this reactor is interesting not only for electricity production, but also for development or using of heat in chemical factories and so on. And so it operates in China. So you have two modules at 250 megawatt thermal power. And this is one of the developments. A lot of countries are interested to replace CO2 energy in chemical industry. The next one I put as an example here, it's a sodium fast reactor. So we have typical type of, as I called, breeder reactors. They are using sodium or lead or bismuth. And there's also going on a lot of research currently in the US. They are built some test facilities. They are building now, preparing test reactors for sodium fast reactors. Here you have also outlet temperature about 500 degrees. And the special way here is you can use uranium much more as in the typical large reactors what we have today. And the most advantaged thing, I call it integral molten salt reactor. Here an example from Canada. What is also in the science certification, you don't have fuel as we know it as pebble or in fuel assembly. So the fuel is in the salt. And the salt is in the reactor. So you have an homogeneous thing of that. And the very special advantage of this one is you can burn up the so-called transuranium elements that you get in normal reactors, plutonium, americium, curium. And these are the elements that have a long half-time. So and it means by using this type of reactors, you can burn the waste. And at the end, you have some waste that has only radioactivity for 300 years. So the idea really here is to use this type of reactors to solve the question of final disposal. And here, microreactor. I put one eVinci, thermal output 15 megawatt thermal. And this is a development, it's currently driven a lot by the military. It comes out of the experience made in Afghanistan, where you have a lot of military sites from the Western countries. We are far away from many cities. And to have electricity there, they're using diesel engines. And to transport of diesel was always attacked by the Taliban. And so comes a request from the US military, first of all, please develop a reactor that fits in a 20-foot container and is remote operable and will deliver it and mix power in 24 hours. So, and this eVinci reactor, this is not in hype, this is reality. The first reactor is now in testing in the Idaho National Lab in the US. But you can also use it in remote sites, not only for military. And there's a lot of development in the US, and especially on the so-called microreactors. And very interesting here, you don't have a liquid fuel. You are using so-called heat pipes for bringing the power out of the core to turbine or something like that. So this is a very interesting development. And they're currently in Idaho National Lab. They have a site available made for the developers, and they will be installed in this year, next year, 5 different type of these microreactors, all there in the range between 1 and 10 megawatt. And this is a new development. And such a reactor, you make it, you get it, and it works for 20 years. No, without refueling, without anything, then you put it back to the factory. Interesting development, but not, I would say, for the large European market. So, but with all this hype, I always like to look on Rigover. This was the father of the nuclear navy, also the father of the nuclear safety culture, I call it. And in 1954, I wrote a very famous paper that say when you want to buy today a reactor, you have 2 types of reactors. Academic reactors and real reactors. And academic reactors are always simple, small, cheap, light, can be built very quickly and very flexible, and there's no development required. You will use only off-the-shelf components. And the reactors in the study phase is not building now. What we have for most of this SMR designs. Real reactors, they are built now, they are behind the schedule, they require an immense amount of development, apparently trial items. They are very expensive, a long time to build, large, heavy, complicated. And this is always my comment on the SMR. Today it looks very, very nice, but you have to start the development and you have to build one. And then we will see if they are academic or they are real reactors. I expect that they are coming closer to the real reactors. So as we heard today in the morning, the European Commission has started this year a so-called European Industrial Alliance on Small Modular Reactors, because EU has seen that we are behind Russia, China, US, and so created this industrial alliance where you have today more than 250. As I have read yesterday, it's more than 300 now. Companies, organizations, regulators, TSOs as part of this alliance. And last week they are selecting 9 designs, which they will look on so-called project working groups for develop of them. Some of the designs I had in this presentation because they are the most favorites. These are not only water-cooled reactors. There's a lot of fast breeder reactors in these 9 selections. And so the European Commission is pressing and spending money for development such of modular reactors not to be on the world market a latecomer. And there's also other things going on next week in Austria and Vienna. It's a big conference on small modular reactors and the applications. So there's a lot of things going on, and there is a willingness on a lot of states for the harmonization, for the standardization, to overcome this cost issue that we have in the comparison between the small and the big ones. And let's come to some of the conclusions. So SMR, first of all, it's nothing new. So we have it in submarines, we have it in aircraft carriers, we have it in icebreakers, we have it in some countries, Russia, China, they have operating SMRs. We have not so much in the Western world. We have one under construction in Argentina, the so-called CARAM design, and the construction of the BWRX 300 is expected to start next year with the first so-called nuclear concrete. All the other preparation work is going on. Today, we have more than 100 design proposals, including these microreactors. I expected that it will be reduced. So we don't see really in construction 100 designs. In the short term, however, I expected only light water reactors because all the other things, okay, gas-cooled reactors in China we have, but fast breeders where you have to use liquid sodium or liquid lead, it's not so easy to handle. And in the molten salt reactors, you have especially the problem that steel and salt, this is something, a combination that it's not too easy to solve, but a lot of countries are putting a lot of money there because this waste burner concept, you overcome this long-term final disposal questions. And this is why a lot of things going on in America. Currently, they are building several test facilities and test reactors for molten salt. And last slide, SMR appears to be suitable for remote areas like in Canada, Alaska, Siberia, where the Russians now constructing 2 SMRs. Far away from electrical grid. The comparison between building an SMR or making 2,000 kilometers of grid lines, so it's cheaper to build an SMR. So we have several sites in Siberia where currently Russian built written 200 S reactors. And Russian trying to sell SMRs to some countries in the Middle Asia. They don't have a big need of energy. Small countries, not a big energy need, and so they're trying to sell it there. But the other interesting thing is the SMR not limiting to electricity production. In Finland, you have now several cities that want to go for district heating by using SMRs. So this is another development we are currently looking in. And yesterday, there was the 5th city announced that they will use SMR, going to use SMR for district heating. And the process heat or chemical industry, when you look on high temperature reactor, gas-cooled reactors, you'll find it there out. The US supports project in Europe and Eurasia as part of the so-called Phoenix project to coal to SMR. Typical around there, when you look on the coal-fire plant, they have installed power 300 to 601 units, 300 to 600 megawatt, and put an SMR there. So that makes available money and is used in Slovakia, I think, and Poland. So to have some project to replace coal-fire plant by an SMR. And this is also just going on in the US. The idea is really you don't need a new infrastructure. You have the grid connection, you have cooling water, so and you can replace CO2 emission of coal by no CO2 SMR. One of the ideas behind. For me, the next 10 years will show whether SMR can reveal the market in a big shape, or it will be a special solution for special cases. We will have it in some cases like Siberia, as I explained, but SMR can really, and part of electricity system in Europe, we will see. There will be always this question about the price. Thank you.